So thanks, Michiel, also for the invitation for presenting here part of the results that we have obtained with one of the ALMA large programs. So it is with the ATOMIUM large program. And so as you can see here in the title, I will discuss a little bit upon one of these results being the fact that we can see the effect of companions, planetary and stellar companions, in the shape of the winds of evolved stars. And so, as you might know, there are various phenomena in our universe which are dictated by the amount of mass that stars lose through their lifetime. So phenomena just as the chemical evolution of the universe, the mass spectrum of white dwarfs and planetary nebulae, the frequency distribution of supernova, the fate of exoplanets. And so in this talk, I will mainly focus on that mass loss rates that stars lose at the end of their life, while being quite cool often, so these AGB stars and the red supergiant stars. And so for a long time, these winds, and in particular their geometry, have been depicted in a quite simple way. Both stars and their winds, as you can see here in one of these Hubble images, were thought to be quite nicely spherically symmetric. And also, so when we were modeling these star targets, when we were modeling these winds, we were thinking more or less in kinds of, let's say, onion-like structures. So if we were thinking upon what is the chemistry, what are the dominant physical characteristics of these stars, you can see this onion-like shells. And for instance, if we were thinking, okay, these stars do have stellar winds, what are the dominant mechanisms? Then we are talking upon how can molecules from dust species, and then we had the interaction with the photons, with the stellar photons, that was, or that is, the driving force for the stellar winds to be created. And so one of these main exercises within stellar astrophysics is then deducing the mass loss rates of these stars, since they are so important for the general understanding of various phenomena in the universe. And as you all know, trying to understand a phenomena can always be done in different ways. You can do it in a purely theoretical way, so the forward models, where you use all kind of theoretical knowledge, benchmark by observations, and you do the predictions. And you can also do, let's say, a little bit different. You do the retrieval approach. You have, for instance, your ALMA data, and you try to model them, but often, and you will see that also here, you will think in the most optimized way. Well, just use your full complex forward model to also analyze your observations, but often this is not possible, just since your models are too CPU intensive. And so if we're thinking upon these AGB stars, these red supergiant stars, just in a schematic way, this is what we should be able to do. We have to think upon what is the gas dynamics, so these stars are pulsating, what are the various chemical reactions that gives our from atoms to molecules, from molecules to dust species, how does it interact with the radiation pressure, so with the photons of the star, what is in general, how does dust and gas also interact one with another. You can see just also from this errors between each of these processes that this is often a non-linear equations that you try to solve, which is not always that easy to be done on a computer. But doing that kind of an exercise, you can come into predictions of your mass loss rate. So given some initial conditions of mass, temperature, luminosity, you can predict then, for instance, what is the temperature throughout the wind? So this is the lower red curve you have here. What is the velocity throughout your wind? And as such, this exercise gives us, and this is now for one particular model, what would be the mass loss rate. Yeah? Now, what is also important for you to see is that this temperature and velocity, they look quite simple. You can approximate them with a power law. And so this kind of a behavior is then used in retrieval approaches. You use this kind of a velocity, this kind of a gas temperature in function of the radial coordinate as a simplified approximation then within your retriever approach. And so then you have your set of observations. You can here see, for instance, carbon monoxide observations. You have your spectral energy distributions. And they are used to deduce for some stars, sometimes for a large sample of stars, your mass loss rate. And if you have a large sample of stars, you can even use that to go into a predictive behavior where you say, given now what I have here, you do your statistical analysis and you say, okay, if I have some temperature, some luminosity, that might be my mass loss rate. And so various authors have done that kind of an exercise to predict in function of stellar parameters what might be the mass loss rate. But however, if you do that exercise and if you compare one with another, this is what you get as an outcome. You see here, and this is a picture I made for a star of a mass of 2 solar masses. And here, if I would assume a star having some effective temperature, you see here how various people have either used a retrieval approach or a theoretical approach. The theoretical ones are the dashed lines. The retrieval approaches are the full lines. And if it's a little bit a mix of both, I've used here a dashed dotted line. Whatever is used, the main message is here is that you see a huge difference between each of these descriptions. You see that actually in 2021, we are not yet able to say or to predict with a very nice, with a good confidence interval, what might be the mass loss rate of a star, of these cool aging stars in function of some parameter. But this is quite dramatic. It's not only for these AGB stars, this is also for the red supergiant stars. But if you don't know the mass loss rate, then you also know that any of your stellar evolution calculations might be highly diverging. And so given some of the outcomes that I just have shown you in the previous slides, these are the outcomes of then what is then the stellar evolution calculation. If you would use the Reimer's law or the Vasiliadis and Hood law or one of these other laws, they just give you something completely different. And we all know that the outcome of evolutionary tracks is a tool which is so often used in all of our predictions. If we want to say something, for instance, on supernova, on black holes, on neutron stars, we always come back to these kind of predictions, but actually they are not very constrained at this moment. What is the problem here? Well, one of the problems is also something that is very clearly shown by ALMA. It is the fact that these stars and their stellar winds are not at all one-dimensional. What I will discuss is only one aspect of it, but we see that these stars and their winds, they do show three-dimensional complexities over different ranges. It goes upon what is our understanding of molecules that form dust grains. It goes upon what is if these stars are pulsating, if they have convections, what are then the turbulences that we see just close to the star, a little bit further out. But the focus of today will be here on this ladder box. We do see large scales, correlated density structures that have a meaning and that we do, or at least we think we do understand that now. So if we are aiming to understand, or at least to have a better prediction of some of these phenomena that I just have shown you, we need to try and we need to have that endeavor, having three-dimensional mass loss rate predictions in function of time. And so, as I told you, this is the focus of today, and this is one of the things we are trying to tackle with the ATOMIUM large project. What is this large-scale density, correlated density structure that we can see here in this wind? And so this was a bit of the introduction. Now I go directly to that ATOMIUM large program. And so for that, I first go back to roughly a century ago. And so what you can see here is one of these first photographic plates that have been made of planetary nebulae. And already then in 1918, Cortes et al. Was wondering, if it once will be possible to really understand the physical mechanisms that is driving all of these complexities that we can see here. And so for more than a century, that question has been open. Since this was so cumbersome, we did see indeed that these AGB stars, and then we had the precursor's, they had such a different geometry from spherically symmetric towards all of these nice morphologies that, for instance, have been depicted by the Hubble Space Telescope. So what have been the causes that had been offered in the past? So there have been various causes: magnetic fields, stellar rotation, or kind of a snowplow mechanism where we had a very fast wind that was plugging into a much slower stellar wind. The cause that was most often in the picture, especially let's say the last decade, was binary interaction. But it was a very particular way of binary interaction, namely binary interaction of two stars that are extremely close to each other, and so that the outcome is that they have a common envelope phase. They have a very short orbital period, lower than 10 days. However, each of these mechanisms, none of them was able to predict all kinds of phenomena that we see. And this is now where ATOMIUM is now coming into the picture. ATOMIUM is an ALMA large program in the field of stellar evolution, and together with some 50 collaborators of all over the world, we are working on that program. And so it was a program of some 113 hours, almost fully completed by now. It is a huge challenge to do all of the data reduction. And the result here is only upon 2 molecules, but we have detected more than 200 molecular lines in the medium configuration, but we have higher and lower configurations. So you see that this is only one result, and we have a lot of results in that large program. And this indeed, the power is in the fact is that you can have a large program with a homogeneous approach towards your sample selection and your observations. And so what do we see in that few data that I will now use for this talk? This is the outcome of these AGB stars. This is what you can see here is a colored picture of carbon monoxide. The red is material that goes away from you, the blue material that flows towards you, and green, why this color is roughly at the stellar velocity. And you see that none of these stars has a spherically symmetric stellar wind. And you can also see that if I show you again this planetary nebulae, that there is a lot of similarity between both the planetary nebulae and then these AGB stars. So this gives us already the first conclusion, namely, it is the same physics that shapes both the AGB winds and the planetary nebulae. And moreover, by looking at these AGB stars, we have caught the mechanisms in the act. So what have we been doing? Well, a little bit partly, this is what we came up with. Since this is the challenge, if you have a large program, we have a lot of observations. How do you deal with that? Well, we came up with a kind of a decision tree. How will we look to all of this data? And for this result that has been published in Science, we have used the 3 steps decision tree, which is based on the CO channel maps, step 1, in which we then look to the kinematics, since if you just have this one-dimensional spherical wind, what we would predict is a wind that has some gradual increase in velocity. But we see also other behaviors. We see targets of which the velocity goes up and then seems to slow down. And in step 3, we have looked to the moment 1 maps and the PV diagrams with a particular focus on silicon monoxides, since that's a very strong characteristic for these velocity fields, quite close to the star itself. And so we then have made a lot of overviewing Excel sheets, I should call it like that. And it was one day that I got a bit, there's too much of information. And on that day, I still remember, I was not working in my office, it was painted during that day. I was working in Connie's office. And I thought, well, I will just use colors. And it was just by using color coding that I suddenly could see that there was a trend in this huge Excel sheet we were working with. And it is a color code that you can see here. Since the targets you can see here, they're not just randomly based, they have been ordered in function of the mass loss rates. And if I was then just using colors just to see similarities, you see that these colors are not random. You could see that what I had red, this was a diagnostic. It is a diagnostic that is linked to having an equatorial density enhancement in the plane. Green ones I could recognize as being have a bipolar outfall, while the blue ones, they had a spiral structure in the stellar winds. So whatever mechanism you are looking at, it was a mechanism that had a correlation with the mass loss rate, and it has a very strong correlation coefficients, the Candle B correlation coefficients of almost 0.8. So of each of these causes that I have presented already to you, which one can now give you a correlation with the mass loss rate? Well, the only one that can do that without having to fiddle too much with the mechanism itself, it is binarity. But it's not binarity only restricted towards stars with a very small orbital period. It is binarity that also includes long period systems with orbits above a year, and hence with orbital separation above 2 astronomical units. So we are talking about binaries, and hence we should understand what is then the effect of these binaries in terms of the Roche Lobes and the gravitational potential. Well, this is, I hope, something that each of you have seen in your master classes, and this has been used also in our community a lot, but there has been a lot of focus in 3 areas. Let's say the detached ones, so stars which are really far away, and then you can talk about the Bondi-Hall-Littleton accretion, so where star, well, if possible, the star can maybe interact via L1, L2, but that interaction is mainly only happening when you come into these other 2 phases where the star fills its Roche lobe and can give part of its material is traveled via L1 towards its companion, and when in this very close encounter, you can have a common envelope. And it has only been much later throughout history that people have filled in a fourth scenario, being a scenario where it is not the star itself that fills the Roche lobe, but it is the stellar wind that fills the Roche lobe. And as such, you can have wind Roche lobe overflow via a channel. It's close to L1, it's not exactly at L1. And if possible, you can have, for instance, have an accretion disk here. Having these scenarios in your mind, you can have various morphologies that you can get. If you have, for instance, 2 stars that are quite mild, that have equal masses roughly, what can happen is that your primary AGB star is wobbling around the center of mass while losing material. And it is that wobble that can give you this spiral-like structure, which if you would look at it face on, the spirals have quite a large extent with respect to here, the orbital axis. If these targets are much closer to each other, the interaction will be much more pronounced, and you can have the formation of what I've told you already, a very dense, quite dense equatorial, you will have an equatorial density enhancement here in the plane. You can see it here. The companion is here at this place. And then you can say, okay, but Leen, this publication was for 1999. Hasn't ALMA seen that already? Sure, there have been already quite a few observations with ALMA and with other kind of instruments that did show indeed that the spirals have been there, and that also did show that spirals are not the only answer, that also other complexities, this is a publication, the heart-like publication of Sophia Remstedt, are visible in the data that we have. But none of these observations was able to deduce a systematic. So we were still in this very scattered understanding of what could be the cause for that. But given already these new ALMA observations from 2012 onward, that had triggered in our community a new effort into understanding that also from a theoretical point of view. And so various groups have started this kind of simulations as if taking into account the impact of a binary companion. And various kind of shapes can form. You can see here one of these simulations where the spiral is caused by the fact that the companion attracts part of the material, and then you get a spiral which doesn't has a wide extent, but a spiral with a very small extent with respect to the orbital plane. And so what we are now doing, since we have now finally also a 3D radiative transfer code developed, which is very efficient, since these are densities, but what ALMA gives us are these observations. And so we should understand going from densities to the observations from a molecule can be quite different. And so we should couple that. And so in the next slide, I will show you a movie. The outcome is this, where you will see in function of time, first of all, how the companion turns around the AGB star and how it creates the shape, the density in the top panel. You see also the C/H2 density, the temperature in the lower panel. And then the next stage, you will see how then given this input, what is then the synthetic observations if you look at it from different inclination angles, and then we will also scroll throughout the molecular line as if you would have a channel map. And I hope this displays now properly. So you can see here in function of time, so this is the time, how the companion shapes the AGB stellar winds. Now we incline it, so you see it's different inclination angles. And now given the inclination angle, 90 degrees, 45 degrees, and 0 degrees, this is the CO line intensity map if we scroll through it as if you would have a channel map in function of the velocity. And this is what we see in the data, but you also can immediately understand that doing the reverse exercise from this kind of morphology towards an understanding of the source, AGB, and its companion, it's a very complex retrieval exercise. So we are now thinking and working on machine learning algorithms to help us in this kind of a quite complex exercise, since we see from the models a lot of morphologies that do arise. We have spider-like morphologies, we have herd-like morphologies, and it's a whole new game that we are starting now. So, but if you don't have that models yet, so are you then sure that it is the mass loss rate that gives you this nice ordering that I was telling you about? That's the first question. But also the second question is, I do tell you that this is binarity, but we don't see the binary companion, with the exception of one source. But in none of them, we see the companion, just since these AGB stars are so bright that these companions are too faint to be seen, even though we are not trying to detect them with other kind of instrumentation. So then the question is how to probe the invisible, how to convince a referee that potentially there are companions there. Well, then you can go back and use population statistics. First of all, what do we know from a statistical point of view? Well, if we look now to publications that do study the main sequence stars and the amount of companions that are detected among stars of various spectral types, I do differentiate here between smaller stars, smaller than 1.5 solar masses, and stars above that. And you see here, based on various publications, how many stellar companions do they have, how many brown dwarfs do they have, how many planets above 5 Jupiter masses have been detected, accounting also for biases. Then I have to understand how much of these sample of companions do I lose when these stars evolve to the AGB, throughout the AGB. And we estimate that we will lose, due to tidal interaction, roughly 10 to 20% of that population. And then the second step is going to population statistics. And it was a point that I didn't realize until we were trying to understand the concept. No, I should say we didn't realize when submitting the proposal, is that we always have had a bias into our AGB studies. And it is this bias being that in order for ALMA to be used and in order for other instrumentation to be used, we need stars with a mass loss rate roughly above 10 to the minus 7 solar masses per year. Otherwise, our signal to noise is often too weak. But if you then use population statistics, for instance, if we look to our sun, and for the sun, when it will become an AGB star, it will only very seldom be in a phase of having a mass loss rate above 10 to the minus 7 solar masses per year. Turn it around.
5 minutes left.
Okay, thanks. So turn it around. What we have here is a bias in our sample selection, being that we have detected that we are mainly studying stars with an initial mass above 1.5 solar mass. And then we go to the upper table, and then you see that if you do the summation there, that on average, stars with a mass above 1.5 solar masses have at least one companion. And then the second step is, since we are now really hardly working on this quite complex 3D hydrodynamical simulations, do you already understand that correlation with the mass loss rates? And so for the publication then in Science, we did the first calculations really in an analytical way. We have taken some corners of the parameter space where we could do the calculations in an analytical way. And from that, we have tried to understand, is there indeed a correlation with the mass loss rates? And we see for different corners in the parameter space, and that's, if you wish, you should read it up, you see indeed that for our, let's say, parameter that indicates how much deviation can you have from spherical symmetry, given the fact that you might have a binary companion, you see indeed that there is a correlation, an anti-correlation this here with the mass loss rate, as also, for instance, an anti-correlation with the orbital distance. The shorter the orbital distance, the more effect you will have, the more disturbance you will have from a spherical symmetry. And then the next step is, okay, we were confident on that conclusion, but then you want to understand some of the impacts of that. And so we have done the calculations of, given now an initial condition of, for instance, an orbital separation, how does that change in function of time along the AGB star? And you can see, this was here one example. The star AGB star had a mass of 1.5 solar masses. And then you can see the outcome in black, gold, blue, and pink for different masses of the companion. You see, for instance, that Jupiter mass companions, they always have the tendency to have a wider separation a lot when time increases. While for more massive companions, they tend to spiral in. And then you will need to understand, okay, but where are now these companions? Well, now we have to rely back on what are the conclusions at this moment, so nowadays, upon companions along main sequence stars. And given that, the conclusion is that most of them, the majority, I don't say all, I say the majority, have an orbital separation above 20 astronomical units. So we are in this regime where most of them, so it means that most companions will widen their orbits throughout evolution on the AGB. And so this gave us a new evolutionary scenario for the AGB morphologies, being that as time increases, we also know that as time increases, the mass loss rate increases. And so this is also the scenario you will have. We will mainly start with disks for low mass loss rate stars. Medium mass loss rate stars, they mainly will have a bipolar morphology, and we will have a spiral morphology for stars with a high mass loss rates. And so this conclusion also gave us a possibility to explain a lot of other results that have been published already in the literature, but that were lacking a general framework. Okay? There are some of them that I have listed here. I will only explain you one. Well, it's not, I know I will not explain that one. I will come to a conclusion to link to some of the other fields that we have been touching upon already today. It is this implication being, you have seen this simulation here. Well, that is a simulation that is fully self-consistent. And given there a companion, you have a mass loss rate of few times 10 to the minus 6 solar masses per year.
And do you mind coming to your summary
Yes,
slide?
I have one more slide, yes.
Okay, thank you.
So what would happen now if I do the same simulation, but without the companions? Since you know companions, they have an impact on the gravitational potential. When, well, without a companion, the mass loss rate is lower by a factor of a few. So it implies that this implies that for single star evolution models, we might have overestimated the mass loss rate consistently if we have done the exercise being the retrieval exercise. Given your observations, how wrong can we be now by neglecting the impact of a companion? And this has a lot of effects in all kinds of simulations we have done. So this is the last slide, sorry for that. So if you're wondering upon the fate of planets, exoplanets, well, if you have a lower mass loss rate, well, the, let's say, academic answer to that is that unluckily, much more, well, more planets will be engulfed by their star when it evolves on the AGB, if indeed these mass loss rates are so much lower. And with this, I would like to thank you, and also I would like to thank the ATOMIUM team.